I've been using ASAP since the mid-1980s. Initially, I was using the program to do straight light analysis on space-based telescopes. Later on, I was using the program to evaluate performance of cockpit displays. Now I'd like to walk through a simple demo that gives the user a general feel for what it's like to work in the ASAP environment. Okay, we're going to be looking at a luminaire system, meaning a reflector, a source, and a screen. Okay. Now, when we construct geometry in ASAP, we have several different options. Okay, we can construct geometry using the builder window, which is a spreadsheet-like environment. We can also use ASAP script, okay, or we can use a CAD program, which is what a lot of our users use. Okay, and that's what I'll do in this example. I'll be using a program called RhinoCAD to construct the geometry. We'll export the geometry from RhinoCAD into ASAP, and in ASAP we'll define and assign optical properties, trace the rays, evaluate system performance. Okay, this is the Rhino environment, and we're going to start by making a model of the reflector. Okay, to do that I'm going to be working with a menu system up here, curve, conic, and during this demo I'm not going to explain every last detail, so this is going to be primarily visual. Okay, so what I've done just now is to create a curved line. Okay, we're going to take that and revolve it around its symmetry axis using the revolve option, using the defaults. This curve we can delete since we don't need it anymore, and we end up with something like this. Okay, an approximation to a simple parabolic reflector, for instance. Now I should point out here that even though Rhino is very intuitive and easy to use, okay, it has a lot of the sophisticated modeling capabilities that more complex CAD programs do. As an example, we can take this surface and do a rebuild. Okay, display the control points and start dragging these guys around like this. Ending up with a much more complex shape. And of course we can export this over into ASAP and use it as a reflector if we want to, no problem. Okay, so let's go back to where we were. Simple reflector. Okay, next we'll construct a model of the filament source. Okay, and again I start by specifying a simple curve. Okay, using the pipe option in the solid menu, we're going to turn this into a solid. Okay, I'm going to temporarily turn the snap option off. Okay, and I'm going to delete the original curve so that we end up with something like this. Now, of course, that filament is too large for the reflector, but that's easy to fix. Okay, we're going to go into the transform menu and do a 3D scale, and then just drag that filament over here inside the reflector. Okay, finally we need to specify the screen. And for the screen I'll use the surface menu plane corner to corner option. This time I'm going to work in the lower right viewport. It's the first corner, second corner. Now, when you use that option, Rhino by default places the plane at the origin, okay, but that's easy to fix also. If we go over to the front viewport here, turn ortho on, and just drag that plane away from the reflector, okay, we're all set. I'm going to do an auto zoom here, and that's what the system looks like. Okay. Now at this point we can export geometry over into ASAP. Define, assign optical properties into the ray trace. However, for complex CAD models, okay, it's much easier to do that if objects are layered according to their optical properties. And just as an example, even though this is a very simple system, I'm going to show how that's done in Rhino. Okay, we're going to go up here to the Edit Layer dialog box, and I only need 3 layers here, so I'm going to delete the last 2, and I'm going to rename these layers. Call the first one Reflector, next one Source, and finally Screen. And then I'm going to place the different objects in their respective layers. Okay, starting with Screen. Screen is already selected. If I click this button in the Edit Layer dialog box, okay, the screen changes color, indicating that it's been placed inside the screen layer. By clicking on this light bulb here, I can temporarily make the screen invisible. Okay. Let's go to the Reflector layer. I select the Reflector, click this button again, and that object has been placed in the Reflector layer. Let's turn that guy off. And finally we have the source. Okay. Now I'm going to do an explode on this object. Okay. And I'm going to place the helical portion of that object into the source layer. Okay, leaving the 2 end caps. Now the end caps will not be specified as emitting surfaces. Okay. If we want to include those in the ASAP model, we can, and will have very little effect on the analysis result. At this point, however, what I would normally do is just delete these guys. Okay, turn all light layers on, do an auto scale, and export the geometry via IGES format. Okay, in the export dialog box down here at the bottom, we specify IGES as the file type. File name will be demo. Click save, and the Rhino IGES export option dialog box appears. Okay. Over on the left, we have a list of target applications. Okay. And inside this list we have Breault Research's ASAP. Okay. That's the option we choose, and the rest of the defaults are okay, so we'll just complete the translation, go over into ASAP, and open up that IGES file that we just constructed. Okay. What we're looking at here is the ASAP IGES translator dialog box. Okay. These defaults are suitable for probably 99% of the geometries you'll ever need to work with, so I'm just going to click OK. And down at the bottom here we have a very simple graphic that helps the user identify objects when we assign optical properties. Okay. In this case, we will assign optical properties to the reflector. Okay, and the way we do that is we highlight the reflector layer here, right click, modify, and if we want to define a new coding, for instance, click on the new coding button, assign a name, ref_b. Over here we have the reflection and transmission coefficients. Okay, we'll assign a reflectivity of 0.95 and a transmissivity of 0. So our absorption is going to be 5%. Okay, and then right here under codings, okay, I'm going to specify the coding that I just defined. Media 1, media 2 will be air. Click OK, and the changes I just made to the reflector are displayed right here. Okay, now with a more complex optical system, you would be repeating this process many times, okay, specifying new coating, specifying new material, glass types, for instance. Okay, or for this very simple system, that's all we need to do. We go into File, Finish to complete the import process, and ASAP will display the script file containing the geometrical information imported from Rhino and the optical properties that we just defined. Okay, at this point we would confirm the geometry by running this script window, going into the System menu and generating a three-dimensional view of the geometry. Okay, this is the ASAP 3D viewer window. There's the screen, here's the reflector, and if I rotate this about, there's the filament. Now if you look closely here, you can see that the reflector looks faceted. That's just a result of the graphical resolution. This has no effect on the actual simulation result. During the ray trace, ASAP will use the curved surface. Okay, so the geometry looks okay. The next step is to specify the light source, and we'll do that inside the builder window, the spreadsheet environment that I mentioned earlier. Okay. The way the builder window works is the user double clicks in the type column, this pop-up window appears, and depending on whether you want to specify geometry, sources, do a ray trace, you would select these different options here. In this case, we're going to specify a couple initial settings. We're going to tell ASAP that we're starting a new system. I'm going to reset some of my environmental parameters. Okay, so after I specify my initial settings, I'm going to import the geometry that I exported from Rhino, and the way I do that is using one of the predefined macros. $read, right here I specify the file name, that was demo, and by default this is an INR file, the script file that I ran just a couple seconds ago. Okay, and finally we specify source properties. We go back into the menu system, raise emitting, and we use the emitting object option to turn that helical filament into an emitting object. Okay, right here we have to specify what the name of that object is. The parameter on the right is the number of rays. I'm going to use the default here. Okay. Now, one thing we need to keep in mind is that ASAP is a surface modeler. Any surface has two sides. Okay. ASAP does not know beforehand which side is best for the user's application. It might decide to emit rays from the inside or the outside, or in the case of a plane, from the left side or the right side. Okay. So what we normally do here is we come in with a small number of rays and we confirm whether or not ASAP has made a reasonable choice for our application. Okay. The way to do that is to run the builder window, come up to the trace menu, trace rays, and to be consistent with the Rhino view, I'm going to specify the horizontal axis as X, click OK, and here's our graphical ray trace, which does not look too interesting, and the reason for that is because in this case the default was to trace rays to the inside of the filament. That's very easy to change. Okay, we go back to the builder window and just put a minus sign in front of the object. Okay, so the geometry is okay, presumably the source is okay. Now we go back into the builder window and increase the number of rays. I'll specify 400,000. Okay, run the builder again. The program is generating rays at this point. Go into the trace menu, trace rays. And at this point, since we have a large number of rays, we do not want to display all of the rays during the ray trace. Okay, that will slow the simulation down a little depending on the graphics driver. So I'm going to use a different setting here. I'm going to tell the program to display only 1 out of every 1,000 rays. Over here, as before, I'm going to specify X as the horizontal axis, and this time when we display the geometry, rather than displaying the geometry as a line plot, I'm going to generate a solid model view of the geometry by selecting plot facets. Okay, so that's the ray trace being displayed. And at the same time, ASAP is propagating rays over in the command output window. It will display ray trace progress. For instance, it took about 19 seconds to trace 50,000 rays. So the total ray trace will take a little longer than a minute. By the way, this is a 2D view of the system. Okay, we can see that most of the rays are stopping at the screen over here on the right. This ray here is not being transmitted through the screen, it's actually passing around the screen. Okay, the ray trace is completed. At this point, we would evaluate screen radiance. And it's important to keep in mind here that with ASAP, the user does not need to specify receiver, detector, or screen before the ray trace. All that can be done after the ray trace. In ASAP, all objects are treated equally in that sense. And to do that, we use an option called Consider, which is found in the Analysis menu right here. Okay, here's a list of objects in our model. I'll select the screen, click OK. And then to get irradiance, go back into Analysis, calculate flux distribution. Okay. This dialog box allows the user to calculate both irradiance and intensity. Okay, irradiance is the default, so I won't change that setting. Down here, the window axes, vertical Y is okay, horizontal will be Z, and finally pixel resolution for the irradiance calculation. In other words, how many pixels are aligned along the vertical axis of the window. I'll use 101 here, click OK. Initially, a spot diagram is displayed. At the same time this is being displayed, ASAP is recording the irradiance value at each pixel on the screen to a separate file. That information can be processed and viewed using the display tools. Okay, display menu, graphics. There are several graphical options here. I'll just use picture, that seems to be popular. Okay, and the display window showing the irradiance distribution appears. Okay, so this is the y-axis, here we have the z-axis, and the units here are flux per square millimeter. Okay, depending on how many rays you've specified at the source, you're going to have different levels of statistical noise in the result. Okay, if we want to reduce the statistical noise in the result, one thing we can do is go back to the builder window and increase the number of rays. Another option is just to average out some of the noise in the display menu. Okay, under processing we have an average option. I'll use the defaults. Click OK, and next we go back into display graphics and generate the new picture. So here's the averaged result, here's the unaveraged result. Okay, so we see that it's significantly smoother if we do a little averaging here. And that's basically it. By the way, this demo is run on an ordinary IBM ThinkPad, no special hardware, 1.8 gigahertz processor speed with 1 gigabyte of RAM.